And we're off. Day 8, lecture number 12. Announcements. Where are the announcements? Certainly not here. Oh, I guess we haven't updated the announcements. Well, I just do them verbally. So you can tell there's some chaos, right? Yeah, the biggest thing is that there's both a homework this weekend. There's also a project that's been released but is not due this week, although there is a checkpoint. So you need to get started on the project this week. Turn in the checkpoint by Friday. That's just the first part of the project, just to get yourself going. And then the whole project is due next week. Hopefully you found a partner already. Any questions about partners or projects or homeworks? Okay, great. I don't think I'm going to tell you anything new today. I thought I'd just go through an extended example of some data analysis so we can get more practice, do a few discussion problems, and then we'll work on new stuff starting on Wednesday. So, quick review. If you want to pick particular columns, you use select or drop. If you want to pick particular rows by their number, take or exclude. Sort the rows. Pick certain rows by a condition. All of this is really just taking a table and picking some sub-table within it. Everything else is about manipulating the table. So you can apply a function to a particular column. You can group rows together. Remember that you can group by one column or you can group by multiple columns. When you group by multiple columns, you get every possible combination of values in those columns. Or you can pivot, which is kind of like grouping by two columns at once, except what's different about pivot, is that instead of getting one row per combination, you get one cell per combination, where the combination is formed by some value for the row and some value for the column. And the last thing we talked about is how you take two tables, T and some other table, and join them together into one table. We talked about that at the end of Friday's lecture. I told you how it works, but never showed you any real examples. Today we'll do some real examples. These are all the operations that you do on tables. You might think, oh, like, how do I do some other cool thing that I thought of? Usually it's a composition of multiple of these steps. Pick out some rows, pick out some columns, join it with something else. Now you have a new table. You can pick out some rows, you can pick out some columns, group those, sort those, pick a column, apply a function, whatever. You can kind of do any sort of table manipulation using these primitive operations. Okay. Now's a great time. Oh, the slide didn't get updated. Criminal. Now is a good time, okay, to take a look at the Python reference that we provide. I'll bet you've seen this in lab, but this contains all of the group and sort along with description. So this is what you're supposed to know about the Python language by the time you make it through this course. Can I turn on the transcript? Yes. There it is. Oh, did it get worse? Oh no, this is good. Okay. Blah, blah, blah. Let's do some practice. Here we go. So we'll load all this. I forgot to mention last time, but we're going to do a lot of trigonometry in this course starting now. So I figured I'd just do a demo. I hope you remember what a sine is and a cosine. And it's actually pretty typical in data science that you're going to take cosines of multiple different variables, use them together in some kind of arithmetic combination so that you can Make it hard. Okay, happy Valentine's Day. I lied. We're not actually going to do any trigonometry in this course. Okay. Just messing with you. Just messing with you. One thing we will do is use joins for value annotation. What does that mean? Well, there's lots of ways you can use joins to combine two different tables to do something you want. But a common one is that you have a data set of all the rows that describe individuals. And then within that, there is some column with a categorical variable x. It's telling you, I don't know, what town something is in. But then you might have information about that town in a separate table. So there could be some second table U that has one row per possible value of x. So here's all the people and what town they live in. Here's a second table that just describes towns, one row per town, with some properties of it, like the population or something like that. You know, town's flag, if there is one. Okay, so if you join t.join on this categorical variable x, whatever its label is, with the table U, which has one row per possible value of x, what you end up with is a table with the same rows as t. You're basically getting a version of t, except now you've annotated each row with all the properties of its x value. Here's a really simple example. Recall that quite some time ago, Swapnil showed you this example of the US Census data set that you can just download from the United States government's website. And in it, it had a column for a population estimate for all people of a particular age, where age 0 means they haven't had their first birthday yet. And then there was this kind of difficult to interpret column 6, where historically the census has always only had 2 options for sex, because this census is collected just by people filling out forms describing themselves. And the question just says, you can answer male or female for each individual in your family. And they use numerical codes to do this. The sex codes, if you group, only come out with 3 options, 0, 1, and 2, 1 row per age group in each of these. But this is like totally inscrutable. What does it mean, 0, 1, and 2? Well, you can go ahead and annotate each categorical value with some information. So here we are constructing a table that has 1 row per sex code in the census, and then a description of what it means. 0 is the aggregate of people who selected male and people who selected female among those 2 options. So you build this little tiny table, you join it with the census table, and the original census table had 306 rows with sex, age, and population estimate. Now we have, again, 306 rows with sex, age, and population estimate, but also we've annotated each row with what the sex code means. It's just like a very typical use of join. To add a little bit more information about what each categorical variable means, or some property about it. Question? Okay, so question about group versus with columns. It's a great question. So figuring out which of these operations to use always involves figuring out what kind of table you're trying to construct, what you have, and imagining what the different operations would do. And then I think each one of these is a little bit different. So let me give you some clues about each. with columns is there just to add more columns to an existing table. This started with an empty table. So when you start with an empty table, you can't group it, you can't join it, you can't really do anything with it except for add rows or columns. So that's why we used with columns here, was just to build this little tiny table, which has no data in it. It doesn't tell you anything about the world. It's just really a description of what these different codes meant in the census. Join and group are actions you perform on tables that already have a lot of data in them. Group is there to have one row in the result for multiple rows in the input. You've got a bunch of different rows about people at different ages. The grouped version might have the sum of all the different ages together. So when you go from multiple rows to one row, that's grouping. And joining is about taking two different tables, the census table that did not have these descriptions, and the sex codes table, which did have these descriptions, and putting them together into one table, which has all the data from census and all the descriptions from the sex codes table. Okay, so there's a question about, like, what if there's other stuff that's not even in the reference sheet I showed you, but it exists? How do we look those up? There is another site I could show you really quickly. Well, if I could get an address bar. If you ever want to see like all of the different things that you can do with a table exhaustively, there is a site for that. data8.org/data science is the documentation for the data science module. And if you go into the table section, you'll see a bunch of things you're familiar with, like num columns and with rows. The nice thing about this is that it's exhaustive. The bad thing about this is it contains things you don't need to know. So ignore it, unless you really want to look up stuff that's kind of beyond the scope of the course, but it's possible. Okay. And there's a question about the column order after you join. That's a nice question. Let's just take a look at this example and explain why we got the columns in this order. Basically, the way it works is you have two different tables. You get the columns in this table, followed by the columns in this table. So since we put sex codes first, we got those two. And then we put census next, we got all the census data. And you could have gone the other way around. Gotten all the same information, except now the census columns come first and the sex code column, which is the definition, comes at the end. Same information either way. So it doesn't matter which table you join first unless you really care about the column order. Okay. That's probably enough. Questions in the room? All right, for the rest of today, we're just going to do a kind of extended demo. I'll ask you some questions along the way. I like this data set. It was when they first started bike sharing, which is like hourly rentals or by the minute rentals of bikes. They didn't start by hiring some private company to operate it all. Instead, there was sort of a joint venture between the Metropolitan Transportation Commission, well, and a company. But the government considered it a pilot, gave some land for this purpose, and then just tracked whether people actually borrowed these bikes or not, and decided to release a data set of all the bike trips that everybody made. You don't know who was on the bike, but you do know where the bike was checked out of and when, where it was returned and when. For every bike trip that anybody took in 2014, 2015. And the pilot was successful enough that eventually they bid out contracts for private companies to kind of take over the service. So I think Ford did it first, and then now it's Lyft. But there's like quite a bit of bike sharing in the Bay Area, which is really great. But no longer is it the case that all of the bike trips are public. Like you can't download a data set of people riding their shared bikes around in 2019 or 2022, but you could for this period between 2014 and 2015. And then there was this cool open data challenge that the San Francisco government ran, which was to say, like, show us something cool. So I like this example. This was, hopefully you can see it. Oh, you can see it pretty well. This is the morning commute where people got bikes and where they went to. And this is like a little picture of the geography of the eastern part of San Francisco where the bike sharing happened. And it's a different pattern than when where people went in their lunch breaks, their evening commutes, and where they went on the weekends. I thought that was cool. So let's mess around ourselves. Here's the table of trips. Each trip gets some random number, the duration in seconds, when it started, where it started, what position in the rack of bikes it was taken from, when it ended, where in the rack of bikes, the bike number, so which bike it was, and then there was a column about people, whether they were subscribing or whether they were just individual use. Questions about the data? How many bike trips were there? Well, we have 3 here and another 354,000 of them. This is a little bit larger data set than we've been dealing with most of the time. So what can we learn about it? I have some. Well, I think the duration of a trip is a pretty interesting characteristic. Let's draw a histogram. I got some crazy warning, and I got perhaps the most useless histogram of all time. Okay, so what is this telling us? What this is actually telling us is that most bikes' trip durations were small, but the scale goes up to some preposterously large number, and that's because while there were many 60-second long trips, there were some really long trips. Where is this person going? Like, if this is a number of seconds, then now we have minutes, and now we have hours. Oh. Now we have days, 200 days. So this bike was stolen. And it's screwing up our data set. So a typical thing you have to do in a real world data set is you have to think about what parts of it you actually care about. That's selecting the rows and selecting the columns. So if we say, I'm only interested in trips that have some like reasonable duration, like 30 minutes. Let's give this thing a name. That's like a commute time. You spend 30 minutes on a bike. We still have 338,000 rows. So that's most of the rows. There were 354,000 before. Why are there so many that are below a half an hour? Well, it turned out during this bike share experiment, if you subscribed, you got the bike free for up to 30 minutes, and then you got charged. So people were racing to get finished within the 30 minutes so that they could ride the bike for free. Just pay their monthly fee. A normal looking histogram. What is this histogram telling us? I'll ask a more specific question. Let's say we have this histogram. We pick some bins that kind of line up nicely. So it looks like we want to go like every 250. That's the range that this thing chose. So let's just go with it. And what are the units here? Well, duration is measured in seconds. Oh, what have I done? Bins equals, okay. There's some bike commutes that are really short. There's some that are almost half an hour, but the bulk of them, the most of the area, is in this range of, 600 seconds is like 10 minutes. That's what this is telling us. If we looked at this histogram, could we figure out what percent of all the people who took it, well, of all the trips, what percent of all the trips had a duration between 250 and 500? How would we figure out that percentage? Is the height of this bar 0.15 times the width of this bar, 250 seconds, is 37.5%. And this is actually a little bit higher than 15, right? It's like, I don't know, something like that. Okay, so it's like 38%. Well, let's actually look at the table and see if that's right. If you look at the commute table, where the duration values are between 250 and 500, how many rows is that? That's that many trips. And how many total trips are there? Well, more. So actual fraction is 38%. And that's kind of what we got. First we got 37 and then we got 39. So right around 38% of the commutes were between 250 seconds and 500 seconds, just like the histogram tells us. Okay, so that's not a surprise. Just wanted to kind of check our histogram practice. Questions? A reasonable question at this point would be, why is the histogram so ugly and blocky? Well, it doesn't have to be. You could draw a histogram of the duration with 60 bins, and then you'd see more detail about the distribution. So now each bin is narrow. You see a little bit more about kind of the shape, which is that there is really this range from 250 to 500, where this is like the most typical trip. But there are lots of trips in the 500 to 1,000 range. It's like a big chunk of the area. And then there's relatively few trips above 1,000 seconds, relatively few trips below 200 seconds. Notice that even though we used a lot of bins, that did not change the y-axis. Because we're using density scale. So even though there's fewer counts within each one, because they're narrower, we have the same amount of density in this range. All right, question? Let's do more stuff. Where do people go? Where do they start? What's the most common start station? How would you figure that out? I'll show you the table again. Okay, talk to the person next to you. This is a 60-second one. How do you figure out the most common start station? Like the name, it might be San Antonio Shopping Center or something like that. We only have one table so far, trip, so it's not join. We sort by a start station. We still just have a bunch of trips. And these are now sorted in alphabetical order. That's not quite what we wanted. We want to group by start station. When we group by start station, actually this actually takes a minute because there's 350,000 of these things. We see for each start station the number of trips that started there. Which is something we could sort by. And then we'll have the most common start station. Which was the San Francisco Caltrain station at Townsend and 4th. Had 26,000 trips start from. If what we really wanted was this string right here, what would we do? We'd first sort. This is kind of like a many-step thing. We'd start with the trip, we'd group, we'd sort. Now we know where the string is, and we can get it out. Okay, let's do the next one. Let's say we want to look at the number of trips between pairs of stations. Well, I think that's a natural use of pivot. If I pivot the start station against the end station, and what it's going to do is create one column per start station, one row per end station, and the value in the cell for a particular row and column is going to be the count. We can see where people went from. When they started at 2nd and Townsend, they went to 2nd and Folsom. Okay, so they just like went down the street a little bit. Or some people went to 2nd and South Park. Some people ended up right where they started. Which actually is a reasonable thing to do. You like go bike somewhere, get a donut, bike back, get back in your car or whatever. Nobody went to Adobe on Almaden. Nobody went to the SAP Center. Why didn't they do that? Yeah, I think this is in San Jose. That would be a pretty long bike trip, maybe like one of those 200-day bike trips. Okay, so turns out that this experiment wasn't just in San Francisco, and even though it's sponsored by the SFMTA, they were trying to coordinate commuting along the Caltrain. So they picked several different cities in the peninsula as well and ran bike sharing there. Okay, what if I didn't want to know the number of trips from 2nd and Folsom to 2nd and South Park, but I wanted to know the average duration? How would I get the same table with the average duration? I'd still use pivot. I'd still have start station on the top, end station on the side. But now in the cell, I would want to put the duration. And when there are multiple different trips, I want to average them. What's interesting about the average duration is it might tell you something about how far apart these things are. So getting from 2nd and Folsom to South Park takes less time on average than getting to Townsend or getting to 5th and Howard. Okay, questions start to appear. Excellent. I'm going to try to answer some of these live. How is a pivot table organized? So this is the result of calling pivot. Is organized by having one column for every value in the trip table's start station column, one row for every value in the trip table's end station column. And in each cell is something about the duration. What about the duration? Well, the average duration of all trips from that start station to that end station. That's how it's organized. What about the order? Well, these are just in alphabetical order, and these are in alphabetical order. Okay. Do you think the average trip time is a good measure of the distance between two bike sharing locations? Look at this table and try to figure out a reason why the average distance is a good measure of actual physical distance, and one reason why it might be a bad measure of actual physical distance. By looking at the numbers in this table. Okay, well, actually, I know that's kind of big, but is this average time it took a good proxy for physical distance, yes or no? Actually, instead of making you talk to each other, I'll let you talk to me. Is there anything that might make you think yes? You need to have some domain knowledge, some geography of San Francisco. Are Folsom and South Park really close together? Yeah, they are. And so it only takes 235 seconds to get from one to the other. This station really is a little bit farther apart. And if you want to go all the way to Broadway and Battery, that is farther. So it seems like the farther someone goes, the longer it takes on average. But there's one quirk, which is that apparently it takes a long time to go from Second and Folsom to Second and Folsom. And that's because people are going somewhere else in between. So I don't think that there's a kind of perfectly simple association between how long an average trip is and how far it is, because sometimes people don't go in a direct line. Sometimes they go like, get a coffee or something like that along the way. Can we fix that problem somehow? Here's how we'll fix it. Instead of looking at the average time it takes, we're going to look at the fastest trip ever between 2 points. Because I think in order to get the fastest time ever, you have to go pretty directly and you have to bike like crazy. Okay, so let's do that. How do we find the fastest trip between each pair of stations? It's basically like what we did before, but instead of showing it in a grid, I'm going to show it in a table with one row per pair of stations using group. Okay, chat's doing its thing. Q&A. I think we're doing okay. Okay, so we could pivot to get average duration. We could pivot to get minimum duration just by replacing this with min. Or we could use group to get the same result in a different format. So what I'm going to do here is select just the columns I'm interested in, which are the start station, the end station, and the duration. And then I'll call that the duration table, simplify my life. We're going to use group. Group by both the start station and the end station. I get one row per pair of places. And I'm going to use min on all the other columns. All the other columns in this case is just the duration column. And that will give me the shortest time between any two pairs. Off it goes. So the fastest time ever between Second and Folsom is 61 seconds. I think in the system there was some limit where after you check out a bike, you're not allowed to put it back until 60 seconds have passed, because otherwise I'll bet somebody would have figured out how to do it faster. So this is probably just an artifact of the checkout system. But now I feel like we're getting a reasonable proxy for distance. Folsom and South Park is really close. Someone made it in a minute. But Folsom to Townsend, you know, someone made it in a little more than 2 minutes. Okay. Look at a few more. Oh. Sorry, I didn't need to recompute it all. What I should have done there is just go to a new cell, because I already did all the work. I just want to show 10. Here we can see some places that are a little bit farther away, like the Civic Center BART took 456 seconds, so a little less than 8 minutes. So here I think is like a good way to measure distance between physical locations, where the distance is how fast can somebody possibly bike there. How is this table different from this table, which was the pivot-based version? Well, one difference is that we only have one row per pair as opposed to a cell per pair. And the other is that this has a bunch of zeros in it, whereas this only contains rows for pairs of stations where someone actually went. Okay, other than that, it's the same information. This is, I think, more useful for most further work. Like, for example, if you wanted to find the 5 stations closest to Civic Center BART by minimum trip time, how would you do that? Here's what you have. There's something called Civic Center BART 7th at Market. We want to find a list of the 5 that are closest to that. Assuming you start at Civic Center BART, where can you go? We'll call it CC. Table of trips, and these aren't trips, these are places you could go from Civic Center BART station. Is take the whole shortest table that we already made. Now we select from it pairs where the start station is the Civic Center. Then we do what? Sort. Sort by this duration min column. Oh, got to show it here. So, fastest trip ever was just to go back to the BART station. Oop, I didn't want this bike after all. Or to go to Powell Street Park, or Market at 10th, or Golden Gate at Polk, or San Francisco City Hall. All these are places that you could get to in under 3 minutes. And then you have to go a little bit farther. So this is kind of telling us something interesting about the world, which is the kind of bike geography of San Francisco. Questions? Yeah. You want to access the individual values, like the names themselves? Sorry, I can't hear you because there's a lot of talking out there. How do you get the individual values, like the names of the stations? Oh, I see. We really want to have these numbers so we can do something with it. Once we have a table with a number in it, we can get a particular column and then a particular item from that column in order to get the number. So let's say I wanted San Francisco City Hall. I could find that particular one. Then I could get column 2, item 0 to get them out. I can tell you meant something completely different, but I don't know exactly what it is. So I think we'll try to solve it afterwards. Okay, so that was kind of all the important stuff. I want to show you something fun, and this will show up again a little bit in your project. Another thing you can do is draw maps with data. So here's a second table from that same data set. The station table tells you for each station where it is in the world and what city it's in. Which is nice because then if you wanted to, for example, get all the stations in San Francisco, and just get particular information. So this is the latitude, longitude. I think it's called long in this table, long. And let's get the name too, the name of the station. Except this mapping software is like a little bit particular. It doesn't like the word name. It really likes it to be called labels. Oh, what have I done? Let's draw a map. Marker, dot, map, table. Once you have a table like this, you just map it. Ooh. Those are all the bike stations. There's that Civic Center BART one. The closest thing was supposed to be Powell Street BART, and it is. The next closest thing was supposed to be, wait, 5th and Howard. That wasn't on the list. Where was 5th and Howard? Oh, it was the 4th closest one. No, wrong table. Fifth and Howard was the 1, 2, 3, 4, 5, 6, 7th closest one. Okay. So San Francisco City Hall and Golden Gate and Market and Fourth are all closer to Civic Center than 5th and Howard. Wait, that one looks farther away. That one looks farther away. That one looks farther away. They're farther away in like straight line distance, but they're closer in bike distance because actually like making this turn is slower than just flying up Market Street really fast. So we've measured something that's a little bit different than physical distance when we've been working on this. But we can still do cool stuff. Like once you can draw a map, you can use all of your other tools to draw other maps. For example, you could try to map all the stations within a 4-minute ride of the Civic Center. So I have the distances in bike duration. I have all the positions. All I have to do is join them together, and I can have all that information in one table. First, I get the places that are close enough. 4 minutes is 4 times 60 seconds. Then I take my map data and I join it on the labels which describe what the stations are called with the list of stations that are close to Civic Center. I have to make sure it looks like something I can map. Curious. How about that? Then I map it. what I get. So instead of all of them, I just got the ones that are close. If I wanted to go a little bit closer, I could go to 5 minutes or 6 minutes. What have I done? I've used a property of join, which is that the result only has rows that match. So if I take all of the different stations and match only with the ones where the name appears in a table that picks only the close stations, the ones that are close to Civic Center, meaning below 6 minutes or 4 minutes or whatever it was, then I end up with a joined table that only has those in it. So let's take a look at this joined table that we made. This was all the information in the map data table, but now we've joined in the duration in minutes, and we've done it in a way that only includes the ones that were close. If we included them all, then we'd have everyone with its duration. But since we picked only the close ones, which were the ones within a 4-minute ride, we got a shorter list. And then when we map that, we got only a few stations. So that means once you have a new primitive, like I can put stuff on a map, you can put anything you want on a map just by manipulating the table in advance. Okay, I think it's pretty clear there's an exam coming in, so let's wrap up a couple minutes early, and I will see you on Wednesday.